symbol, typically the symbol for current is a capital I. Typically this is a DC current. AC current is a lowercase I. I've always assumed that they use the letter I just because it's generally straight, especially without the serifs. You know, like current flows in a line, it's a line.
What's the C in DC?
What, sorry?
What's the C in DC?
It's direct current and alternating current.
Yeah. And even though current is repeated twice, alternating current is a thing by itself, and then there's alternating AC voltage, AC current, AC, and so forth. Impedance, inductance, etc. It is defined as the rate at which current passes by a particular spot. So if I have a wire here, and I look and see how much current is passing by in a certain amount of time, if it's a steady amount of charge per unit time, then I have a steady current. So if I have a current of, well, before we get to that, unit-wise, since we're mainly concentrating on DC, the SI currents, the SI units for current would be the SI units of charge over the SI unit of time, which would be
Coulombs per second.
and that should be a lowercase s. Now, coulomb per second is too much for physicists to write, and so they came up with the shorthand, which I think was mentioned last time, the ampere. Technically, ampere is the base unit, and coulombs is the derived unit, but generally not presented that way in textbooks. So let's just do an example. I have a current of let's just say I've got 3 protons passing by this every microsecond. What is my current?
So it's 3 times the charge of the proton over 1 microsecond.
So my current is the charge that passes by. So that's 3 times 1.6 times 10 to the negative 19th coulombs, divided by 1 times 10 to the negative 6th. And so that's 4.8 times 10 to the negative 13th amperes. That's a small current. So let's play around with this a little bit.
I have a question.
Oh, yes.
Is current always positive or can it be negative?
All right. It is not a vector, first off, but it can be negative. So current is defined as the direction of current from the high potential to low potential. Again, this goes back to Franklin, and just as he didn't know, since positive charges flow from high to low, this would also be the direction of positive charge flow. And I'm going to try to write in some language which will be recognized. Positive charge flow. Or opposite the direction of negative charge flow. Now, most of what we do, so much writing into recognizable language, most of what you will deal with, it's going to be the electrons that are flowing, and so you can generally think of it as opposite direction of the electron flow. If you get into higher energy physics where you're actually shooting positive particles, then it's in the direction of positive charge flow. You take a hydrogen atom, expose it to an electric field, strip the electrons away from it so you got a proton, and then you collect enough of them, and then you shoot them at a target. The other way that you will see it is that if I have a wire here, and I have an electron flowing to the left, as mentioned before, there's got to be some place for the electron to go. So you have an electron flowing this way, leaving a hole, and then an electron flows in to fill that hole, which leaves another hole, an electron flows that, leaves another hole. So I have my electron flowing that way, which means I have a hole traveling that way. And I have seen some physicists present this as in like having a positive hole flowing that way. So absence of electron is a positive charge. It works for the solid state people. Personally, philosophically, I just have an issue with it. But you might see lowercase h plus, and that's just a hole that happens to be traveling opposite direction of the electrons, because electrons keep filling in the hole. Solid state physicist. It's a zany bunch.
So does that mean if you asked us if there were 3 electrons instead of 3 protons?
Say it again?
If there were 3 electrons passing in 1 microsecond instead of 3.
3 electrons going that way?
Yeah.
Would have the same answer as there's charge flowing that way. Now, that's right, your question about negative flow. So here we have our current flowing this way of that, so 0.48 picoamperes flowing to the right. You can also treat it as negative 0.48 picoamperes flowing to the left.
So you just change the sign.
Yeah, so you flip the direction, you just make it a negative. The reason why it is not a vector is that if I have a charge flowing into a junction, going back to something Kyle said earlier from last week, current in equals current out. So if I have 3 amperes flowing in here and 1 ampere flowing this way, how much current is flowing down this path?
2.
Yeah. If I have 3 amperes flowing in this way, and then 1 ampere flowing that way, how much is flowing this way?
2.
Yeah, it's the same question. The orientation of these is completely irrelevant. There's no direction. The direction of this current is not affected by the fact that, they're now going this way. So even though there is a negative value, it is a scalar quantity. Right. Did I add? Okay. Other questions up to here? All right, fun with current. Now what's actually moving are, there have to be charges that are moving. So I want you to define capital N as number of, we'll just say free electrons. And these are electrons that are going to flow. Some electrons will be stuck to the nucleus. It's not like every electron in the copper wire is going to be moving. The mess of electrons still trapped with the nucleus. But there are some which are floating out there which can easily move from one place to another. I want to define lowercase n as the, call it charge carrier density. And this would be the amount of charge per unit volume. I guess I'll stick with big Q right now. And so the amount of charge, the charge would be N times V. So if I wanted to, actually, I do want this to be a lowercase q. Sorry about that for those who are taking notes in here. Because if I want to know the total amount of charge that can flow, and then big Q would be N times little q. It's the number of charges times what one individual charge is, which is the charge carrier density times the volume times something got way whacked there. Q equals. I'm gonna have to edit this out. I'm gonna mess up. To charge carrier density, lowercase n. Oh. You might want to just sort of draw a line under that stuff, and let's try that one again. That never happened. All right, so probably charge carrier is a better word. Number of charge carriers. That's pretty much the same thing as I had before. I just give it a slightly different name. Lowercase n is the charge carrier density. It's the number of charges per unit volume, not the charge per unit volume. So this is number of charge carriers per unit volume. So if I want to look at the entire charge flow, this would be the number of charges times the charge of each of them, which is n, little n times capital V Q. There we go. If we're looking at differentials here, because ultimately we've got a dq right there, we have the differential of Q is going to be N Q times the differential of the volume. Because the charge carrier density is just a ratio, it's relatively constant for a particular material. Q is the charge of whatever the charge carrier is, and so volume is the one that we can play around with, that we have a differential. So dq dx, actually let's draw a picture here. So if I take my wire, this has some cross-sectional area here. Cross-sectional area. Actually write out the word cross. And we'll just make dx is that sort of the depth piece of it. So dq would be in q, well, my volume there is just my cross-sectional area times dx. And then, therefore, dq dx equals nqa. So let's think about the electron flow here. We have an electron that's zipping along, and the way I usually have characterized it up to here is that you have these charges that are just passing right along. You know, picture big open pipe there and just stuff zipping down. And in higher energy physics, we pretty much get to do that. However, since most people don't go into high energy physics, let's think about what we have here. We have copper wire and aluminum wire. The electrons don't just flow naturally in a straight line because they keep running into things. So I have an electron. So if this is my wire right here, an electron flowing this way, it's going to hit something and bounce. It's going to hit something, bounce. Maybe hit something there, bounce. One of the reasons why it takes a while for an electron to make it through a single electron to make it through a circuit, it doesn't take long for in essence, the holes to travel. But for looking at a specific electron, it takes a while for it to make it all the way around. The speed at which this electron is traveling, ultimately, is known as the drift speed. In superconductivity, it is more of a straight line, but for practical use, it does not travel in a straight line. And that would just be dx dt. So from this equation right here, we have dq dx times dx dt is equal to nq a times the drift speed. That's a q there. I have dq dx times dx dt. Well, the dx's cancel out. What I'm left with over on the left-hand side is dq dt. It's equal to nqa vd. And what is dq dt? So we have a formula here for current if we know what the charge carrier per unit volume is, or the charge carrier density is for a particular material. Most likely the charge here is an electron. Cross-sectional area, well, that's manufacturing specs for the wire. And then drift speed is sort of a nebulous thing at the moment. Playing around just a little bit longer. I'm going to divide both sides by the area, so I have NQ, slowly fading there, NQ times the drift speed is equal to I over A. Current per unit area for cross-sectional area. And this, of course, has a name represented by the letter J, capital J. This is current density. Now, for almost everything that we do in this course, we assume that the current density is constant over the course, over the area. So if this is my wire right here, ignore the hole, just assume it's solid. This is my wire right here. I'm assuming that the current flowing at this spot is pretty much the same as the current here, current here, current here. The current's pretty much the same no matter where I am. In reality, current doesn't behave that way. Current at the edges, well, think about a river. Current at the edges does not flow the same as the current in the middle. In terms of electrons and current passing through a wire, current in the middle has more paths to take to get around an object than the currents on the side. Current on the side is limited. Because current is not like fish, flying fish that are just going to jump out and land back in. It'd be a cool effect, although I suspect it would be incredibly dangerous. So we can generalize this current density, the IDA. And I've seen the textbooks, various models. I did not pursue electrical engineering enough to get into the practical aspects. Sorry, Lawson. But you can think of a wire this way. If the current's flowing in that direction, you can think of it as, it's not unreasonable for this to sort of be a plot of current density versus radius. That the higher current density up here than here. Because, well, not as much current flows on near the edges as it does in the middle. And with that, I think we're gonna have to say farewell. I'm glad all of you are here and are safe, and let's hope we maintain that. Daniel.
With the quizzes for chapter 27 being marked, with the quizzes for chapter 27 being marked.
The quiz for chapter 27, we'll go ahead and establish it now.
I mean, doesn't matter to me.
Well, what is this,
I think it's the second. Yeah.
this is the second is here. Hey, you just take the test and then are you good with the quiz the Tuesday after the test, or do you want, or push it off longer?
I mean, I was asking,
I would rather finish it.
I mean, we can,
I do it a week after.
week after the test, so
Yeah.
that day?
Yeah,
Yeah.
please.
Yeah, and
I'll
also
make
the
sure that's
master
short.
set for that.
Or the masters.
The master, can the master set for that be the
The
next
Tuesday
Thursday,
after?
the
So we're gonna
Thursday
get
after
off on that.
The next Thursday after.
Yeah,
Let's stick to Tuesdays, so, eventually get another piece of paper up here, so we'll start on the 27 quiz here. We might double up 27, 28, something like that. We won't officially write it, but I'm expecting, I don't wanna do it right after the test. When is spring break?
Oh, wait.
Does, is
So I
it?
don't know.
It's the week of the
Yeah,
16th.
I don't know when.
Week of the 16th.
I think so.
No idea.
So, we got that, so there's a week after that, and then there's spring break.
Yep.
All right, we'll worry about it later.
Spring break.
Everyone tonight. Bro, 144.
Oh, yeah.
Good evening.
You do, Marisol.
Thank you, Dr. Fox.
Yep.